In this video, I will demonstrate how to perform factor analysis. Factor analysis is different from many of the other techniques that we've learned. It's not designed to test hypotheses or tell you whether one group is significantly different from another. It's really designed to be a data reduction technique. So it takes a large set of variables and looks for a way that data may be reduced or summarized using a smaller set of factors or components. It does this by looking for clumps or groups among the intercorrelations of a set of variables. This is an almost impossible task to do by eye with anything more than a small number of variables, but this technique allows you to do this with a large number of variables. This family of factor analytic techniques has a number of different uses. It can be used extensively by researchers involved in the development and evaluation of tests and scales. The scale developer starts with a large number of individual scale items and questions, and by using factor analytic techniques, you can refine and reduce these items to form a smaller number of coherent subscales. Factor analysis can also be used to reduce a large number of related variables to a more manageable number prior to using them in other analyses such as multiple regression or multivariate analysis of variance. There are two main approaches to factor analysis that you will see described in the literature: exploratory and confirmatory. Exploratory factor analysis is often used in the early stages of research to gather information about or to explore the interrelationships among a set of variables, and that's what I'll be demonstrating in this video. Confirmatory factor analysis, on the other hand, is a more complex and sophisticated set of techniques used later in the research process to test or confirm specific hypotheses or theories concerning the structure underlying a set of variables. In order to understand some of the terminology we'll be using in this particular analyses that causes some confusion involves the use of the word factor, which can have different meanings and uses in different types of statistical analyses. In factor analysis, it refers to the group or clump of related variables. In analysis of variance techniques, it refers to the independent variable. These are very different things despite having the same name, so making sure you keep that distinction clear in your mind when you're performing the different analyses, especially when we're talking about factors in factor analysis. So there's different steps involved in factor analysis, three main steps. And the first is assessment of the suitability of the data for factor analysis. So there's two main issues to consider when determining whether a data set is suitable for factor analysis. The first is sample size, and the other is the strength of a relationship among the different variables or items in a survey or some sort of an instrument. While there isn't a whole lot of agreement among authors concerning how large a sample should be, the general recommendation is the larger the better. And it's because in small samples, the correlation coefficients among the variables tend to be less reliable, tending to vary from sample to sample. So factors obtained from small data sets do not generalize as well as those derived from larger samples. We generally think about sample size not so much as the number of people relative to a population, but really the number of samples relative to the number of factors. So when we think about that, we think about it in terms of a ratio. So we usually think of this in terms of the ratio of participants to the number of items that we have. So a lot of authors will recommend a ratio of 10 to 1, so 10 cases for each item to be factor analyzed. Others suggest 5 cases for each item, but typically you can't go wrong with having a slightly larger ratio of 10 to 1 is typically what I would recommend. The second issue is the strength of the intercorrelations among the items. Typically, you like to have the correlations between the items be greater than 0.3. If there are very few correlations above this level, factor analysis may not be appropriate. And there are a couple different ways we will assess that, as you'll see as we go through the analysis process. There's a couple of tests involved that will help us determine if we have an adequate level of intercorrelations among our items. The next step is known as factor extraction. This involves determining the smallest number of factors that can be used to best represent all the interrelationships among our variables or our items in a questionnaire. There are a variety of different approaches that can be used to identify or extract the number of underlying factors or dimensions. Some of the most commonly available extraction techniques are principal components, principal factors, maximum likelihood, unweighted least squares, to name a few. The most commonly used approach is principal components analysis, and I'll be demonstrating that particular approach in this video. And this involves balancing kind of two conflicting needs: the need to find a simple solution with as few factors as possible, and the need to explain as much of the variance in the original data set as possible. And again, there are a number of different techniques that can be used to assist in this decision making, and we're going to use one called Kaiser's criterion in order to determine this. So using Kaiser's criterion, we look at factors that have an eigenvalue, which is an indicator of their suitability of 1.0 or more, are usually retained as part of the model. And so the eigenvalue of a factor represents the amount of the total variance explained by that factor. The third step is known as factor rotation, and then we get into the interpretation. So once the number of factors has been determined, the next step is to try to interpret them. To assist in this process, the factors are quote-unquote rotated. So this doesn't change the underlying solution, rather it represents the pattern of what we call loadings in a manner that's easier to interpret. So what it does, it just tries to show us which variables seem to clump or go together best. So from your understanding of the content of the variables or items that you're working with, and of course the underlying theory or past research, it's up to us to interpret possible explanations or interpretations. So there are two main approaches to rotation, resulting in either what's known as orthogonal or uncorrelated or oblique or correlated factor solution. We typically are going to use an oblique approach, and this allows for the factors to be correlated. In practice, the two approaches often result in very similar solutions, particularly when the pattern of correlations among the items is pretty clear and has a stronger correlation coefficient. Okay, let's get into an example here. So we're going to be using some data, as you can see on the screen, in which we have our research question, or what we're trying to accomplish here is trying to understand the underlying factor structure of a scale, the positive and negative affect scale in this example. So past research suggests a two-factor structure for this scale, positive affect or negative affect. And so we want to find out, using our sample that we've collected here in this data set, is the structure of the scale in this study using a community sample consistent with previous research. And so we have a set of correlated continuous variables, items on a scale. There's 20 of them, 1 through 20. And so what we want to determine is, does factor analysis, can it identify a small set of factors that represents the underlying relationships among these groups of, assumed related questionnaire items. And so again, the assumptions we have in order for factor analysis to be appropriate is, we want to have, probably since we have 20 items, we want a sample size to be at least 150, so we have a ratio of at least 5 cases for each of the items or each of the variables. And again, we want the factorability of the correlations to be, in other words, for these items to be suitable for factor analysis. We want to see correlations of 0.3, R values of 0.3 or greater, and we want to look for as many of those items as possible. Because factor analysis is based on correlation, it's assumed there's at least the relationship between the variables is linear. It's really not practical for us to do scatter plots of all these to make sure they are linear, but you can spot check them. And the other assumption we have here is that we've already screened the data to be complete, accurate, and normal, because we want to make sure we do not have any outliers in our data set. So we want to make sure that because factor analysis can be very sensitive to outliers, that we've eliminated any outliers that could be skewing any of the items in our data set. So let's go ahead and get into the procedure then. So we have our data set, and our first step is to go to the Analyze menu, or the Analysis menu. And we're going to go down to the Advanced drop-down menu, and you will find Exploratory Factor Analysis. So we're going to go ahead and click on that. Now, there's a couple of options that we need to set, or you need to make sure are set. So we're going to click on the Options button first, and we're going to look at some of these different things. So we want to set an alpha level. This is which we're going to test for significance. We can have that set at 0.05. We need to choose a rotation method, and we're going to choose the Abilene model or method. We also have to choose a factor extraction method, and we're going to use the maximum likelihood method. And we want to make sure the multivariate plots, the factorability test, and the multicollinearity test are all enabled. So now that we've got once we have all those situated, we can save those options. Okay, our next step then is to choose our variables. Okay, and so the variables that we are going to choose are labeled PN 1 through 20. So those are the items that are in this this scale that we want to study with the factor analysis. So we want to click the Add Modify Variables button, and you can see our PN variables here. So we're going to go ahead and click on all of those. So we have PN 1 through 20 selected. Those are the items in our survey or in our measurement tool. So once we have all those selected, we go ahead and click Confirm. And then the next thing we want to deal with is the factor selection method. And so we want to click on the Add Modify and go to our drop-down menu. And as I mentioned before, we're going to use the Kaiser criterion. So select that and then click Confirm. And then go ahead and click the Calculate button. And so it might take a few seconds for your analysis to occur. But now we can see here we have our interpreted output. So as we begin the interpretation, we're going to use the raw output to start with, so that we can look at some of these different tables and some of the output that we're then going to interpret. So our first step then is to determine how many components or factors we'll be able to extract. We need to look at a few pieces of information provided in the table that's labeled Kaiser criterion. And so we're only interested in the components that have an eigenvalue of 1 or more. So what we're looking for is the observed eigenvalues column to start with. And so we want to scan down here and find the components that have eigenvalues above 1.0. As we can see here, only 2 factors are above that criterion of 1.0. And so these 2 factors, or these 2 components together, if you look at the last column, explain about 88.5% of the variance within this tool. So we can see here that we've got 2 factors that explain a large amount of the variance. Okay, another thing we can look at relative to the Kaiser criterion, a lot of times when we have a lot of components that seem to have an eigenvalue above 1.0, there's one way we can kind of double check that, and that's to look at something called the scree plot. So if we go to the interpreted output and scroll down, we can see this figure 2, the scree plot with the Kaiser criterion. And what we're looking for is kind of a change or an elbow in how this graph is laid out. So we can see a bunch of components here below that 1.0, and at this kind of inflection point, any points above 1.0 are the points that would be appropriate to include. And we can see a very clear break here between the second and third components. And so components 1 and 2 explain or capture much more of the variance than any of the remaining components. And so depending on your research context, some of these others might still be worth exploring, but remember, factor analysis its primary goal is a data exploration technique. So the interpretation and the use you put into it is up to your judgment rather than really any hard or fast rules. But at this point, we can see that we have two components that seem to be explaining the large amount of the variance. The next step in the interpretation is to look at what are known as the factor loadings. And so this refers to determining which of the individual items load more on or belong more with one factor versus another factor. And so we're going to look at each of the values here in each of the columns relative to each item. So if we can look at the first one here, we can see that item number 1 has a higher value, 0.65, for factor number 1, which means it loads more with this particular component of the survey. If we look at the item just below it, it has a very low value, a very low loading value for factor 1. But if we go to the next column, we can see that item number 2 loads quite well on factor 2. So what we're looking for here are patterns to say which items seem to go together within a factor. So as we look at factor 1, we see that item 1, item 4, items 6 and 7, for example, all have fairly high values. The closer to 1, the better, and above 1, the better. But as we can see here, we've got a few questions that all seem to load well with factor 1. If we look at the next column, factor 2, we can see that item 2 has 0.64, item 3 has 0.73, item 5 has 0.40, and so on. So those are the items that load well with the other factor. And so we want to look for those patterns and identify those patterns, and then we can go back to the original item and what it might be asking and what it might represent. So you could say then that if we look at factor 1, that item 1, 4, 6, and 7 are all measuring the same component within your tool. And if we look at factor 2, a different component, we can see that item 2, 3, 5, and let's say 8 are all measuring the same component, are all kind of loading together. And so that's when we start to be able to tease out which questions are measuring the same aspect or the same component of a given construct. And they might be opposite constructs. In this case, the example, we're looking at negative affect and positive affect. So we can see that questions are kind of diverging from one another and falling under one factor, positive affect, or another factor, negative affect. And so we can start to see how these factors load, how they go together, measuring one component versus another. Now we might run into situations where there's a question that doesn't load well on either factor. And so how we determine if that's happening is we look at the communality column, and what we're doing here is looking for values below 0.30. So if we've got an item that has a communality value below 0.30, then that tells us that's not really loading very well in either factor. And so those are the items that you would look at potentially removing, or looking at how they're written and trying to refine them, because we want to try and get our tool to be as efficient as possible So if we have to eliminate some questions that don't really seem to be measuring either factor, in this case very well, it would help to eliminate those. So as we look at item 4, it has a low communality value, 0.22. Item 5 also has a low communality value. And we can do that for some of these other items. And we can probably find a couple that fall below that 0.30 value that we might consider removing from our tool because they don't seem to be measuring either factor very well. And so that's one way we can begin to refine our tool. And that is essentially the process. So then once you remove some of these items, perhaps you might rerun the analysis and see how that changes your factors. Do you have 2 factors or does it become 3? And then look at how each individual item again is loading, and that begins to again tell you what what aspect or what factor each item is measuring or representing. And then one last thing in the raw output that we can check to determine the utility of our tool that we have here relative to the loadings is we can actually look at a chi-square goodness of fit test, which will give us an idea of the statistical significance of our tool and its ability to measure either of these 2 factors. And we can look at the p-value, and that can give us an idea of how, the strength of that model. In other words, it measures the construct we want to measure better than chance. As we can see here, the p-value is quite a bit less than 0.05. So that tells us there's a good fit, there's a good commonality, there's a good loading pattern for each of these items relative to our 2 factors. And so that is how we would then assess the utility of our items within our tool, and that's how we could then determine how we might need to change the tool, perhaps to revise it, to try and make the loadings as clear as possible and make the shared variance be as large as possible as far as the variance that can be explained within each of our factors and within each of our tools. So hopefully you found this to be useful. This was a fairly clean data set. It doesn't always turn out quite this clean. And oftentimes we might have a situation, in which the variables or the items load moderately on a number of different components, and some components might only have 1 or 2 variables or items loading on them. And so in this case, you might need to, again, look at some of these commonality values to decide if we need to change the items or remove items in order to make things a bit more clear. And so there is a certain amount of trial and error in this as we look at some of these different components and as we look at some of the items that load onto those components. So that's why it's referred to as exploratory factor analysis, because there is a certain amount of exploration involved here. But hopefully you found this to be useful, and this could be a technique that you can utilize in your own research.